now we're going to talk about how do we measure radiation. So we'll be looking at some quantitative aspects of radioactivity. So the instrument that is used to measure radiation that is emitted from something that is unstable is called a Geiger counter, right? And this is usually used to indicate or detect beta and gamma radiation. And what you're looking at here, this is an actual Geiger counter right here, but this here is basically a schematic representation of what it looks like. And basically what you do is that you point this cylindrical object at the radioactive material, and the energy and the particles that is emitted from the radioactive material enters through this window here. It ionizes a gas inside here. Usually the gas is argon, if I remember correctly. And it forms ions, and those ions result in an electric current that is led to this counter right here. And this is the meter, which basically indicates each time an ion is formed, it basically indicates that on the meter, right? So it literally counts the number of radioactive particles that is emitted from the radioactive material right here. All right. So basically, directly from such a measurement, we can determine the amount of what we call Curie. This is basically a unit of radioactivity, and it measures the activity as a number of atoms that decay in 1 second. So for every 1 second, whatever the number of atoms that decay, that would be the amount of Curies. There are some other units here which is in relation to the effect of radiation on the tissues of biological system. There is the RAD, the radiation absorbed dose, which is measures the amount of radiation absorbed by the tissues of the body. And then there's the REM, which is measures the biological damage caused by different types of radiation. All right, so those are different from the Curie. Okay, and this is just basically a table showing you some units of what we just talked about. As far as the activity is concerned, as I mentioned before, we have the Curie, and that is actually equal to 3.7 times 10 to the 10 disintegrations per second, right? And the SI unit for radioactivity is called the Becquerel, BQ, which is 1 disintegration per second. So basically, so therefore we could just simply replace this unit right here with the BQ unit, and that would be equal to 1 Curie. And then we have the unit for RAD, which is the gray, and then we have the unit for biological damage, which is actually a function of the RAD, as you can see from this equation here. It's the RAD times a particular factor. This factor actually depends on the type of radioactive particle. I don't remember exactly what the numbers are, but the alpha particle will have a factor which is different from that of the beta particle, and so on. And the SI unit is the sievert or SV. Now, basically, believe it or not, we're all exposed to radiation every day. It all depends on, where we are on Earth, but basically you can't avoid it, right? Now, so therefore, as stated here, the exposure to radiation can come from naturally occurring radioisotopes, or if you have undergone some medical or dental procedure like x-rays and so on, and then air travel, believe it or not, if you go higher up into the atmosphere, you're closer to the sun, which produces radiation, and you're less. And if you go beyond the ozone layer, which protects you from the harmful radiation from the sun, then you'll be exposed to those types of UV radiation, which can cause some damage to your tissues and so on if you're exposed to it for too long. There's a radioactive element that occurs naturally known as radon. I'm not sure if we have that issue in Florida, but I remember when I was living in the DC metro area, I remember seeing adverts on TV talking about, making sure that your house is checked for radon, because apparently in those regions, radon basically is naturally produced. And then from smoking cigarettes as well. And in fact, this chart right here basically gives some numbers for the amount of radiation that is received by the average person in the United States. And it give you a breakdown as to the different sources of radiation, from the natural to the medical and others. All right. Okay, so here's a question. This question says a typical intravenous dose of iodine 125 for a thyroid diagnostic test is 100 microcurie. So the question is, what is this dosage in megabecquerels? All right, and it gives you the relationship between the Curie unit and the becquerel unit. Okay, so basically, let me turn on my pen function here. So what I would do is start off with the 100, let me write it here, 100 microcurie, and I would convert that to curie. Now micro is 10 to the 6, if you look it up in the chart that I've provided for you in Canvas. So therefore I would put, well, micro is 10 to the minus 6, I'm sorry. So I would put 1, or let me put 10 to the minus 6. No, I'm sorry. 1 microcurie. Let me erase this here. Sorry about that. So I would put here, I would put 1 microcurie down here, and 10 to the minus 6 curie above. And then the next conversion factor is where I would do the relationship between the becquerel and curie. So 1 curie down here, and 3.7 times 10 to the 10 BQ here. And then I need one more conversion factor. I wish I had the space to do it across, but I'm going to do it down here. And this is where we're going to go from becquerel to megabecquerel. So 1 megabecquerel would be equal to 10 to the 6 becquerel. So basically, this unit will cancel with that. That unit will cancel with that. This will cancel with that. And we do the number crunching. So let me do that now. 100 times 1 times 10 to the minus 6 times 3.7 times 10 to the 10 divided by 1 times 10 to the 6. And according to my calculations, the answer becomes 3.7 megabecquerel. All right, so that's this option right here. Okay, so that's basically how that is done. All right. Okay, the next topic I'm going to talk about some more quantitative aspects of this topic, nuclear chemistry, and that has to do with this concept of half-lives. I'm sorry, half-lives of radioisotopes. So let me go to full screen, and let me define first what we mean by this term half-life. So the half-life of a radioisotope is the time taken for the radiation level to decrease to 1/2 its original value. Another way of stating it is the time taken for a substance, a radioactive substance, to be reduced by half upon emitting radiation. All right. So an example of this would be iodine 131. So let's say you start off with 20 grams of that. So after 1/2 life, the mass will be reduced from 20 to 10. And then after another half life, the mass will be reduced from 10 to 5. And then for another half life, the mass will be reduced from 5 to 2.5, and so on and so forth. So basically, after each half life, there'll be a subsequent reduction of the amount of the radioactive material by a half. All right. Now, what you'll find is that different substances have different half lives. But before we get to that, here is a plot of the amount of the the amount of the radioactive material that we saw in the previous slide, which is iodine 131 versus time. And you see basically what happens as time progresses. So in the case of iodine 131, the half-life seems to be 8 days. So after 8 days, the amount of iodine 131 reduces from 20 to 10, and then after another 8 days, reduces to 5, and then after another 8 days, it reduces to 2.5, and so on and so forth. All right. And that is basically what is being shown here numerically. And then as far as the product is concerned, you can see the amount of product that increases accordingly. All right. So as I was saying earlier, different radioisotopes have different half-lives. And these times can vary from seconds to billions of years, right? I mean, there's really no limit, so to speak, in terms of the possibilities. So in the case of carbon 14, its half-life is measured at 5,730 years. But when you look at potassium 40, its half-life is 1.3 billion years, right? So there are some substances that have very long half-lives, and there are others whose half-lives are relatively short. And what you'll find is that in terms of medical usage, they tend to use radioactive isotopes that have relatively short lives. When I say short lives, half lives, I'm talking like of the order of hours or days. All right. Um, Naturally occurring radioactive isotopes, they tend to have longer half lives in the years and thousands of years and billions of years and so on. So, for example, uh, we have a radioactive isotope. They didn't say what it was, so we don't know. Anyway, we start off with 40 milligrams of this, and after two half lives, 10 milligrams will be left because after the first half life, the 40 is reduced to 20, and then after second half life, the 20 is reduced to 10. So therefore, this is basically how you can calculate the amount that would remain after how many half lives, right? You start off with 40, and let's say you want to find out how many would remain after two half lives, you multiply it by half times a half.